Hey there, Focus Learners, and welcome to today's Explainer. We have a super exciting and really clear goal for today. We are going to map out the complete chapter concept on the Earth's internal structure, and we'll be making sure to include real-world examples for every single topic we cover. We're going to take all the core facts, the diagrams, and those examples from your material and structure them so you get the absolute complete picture of what is going on right beneath our feet. So let's dive right in.
To kick things off, I want to pose a really fundamental investigative question. It's actually one that might have already crossed your mind. If nobody has ever traveled deep inside the Earth, how do we actually know what's down there? Like, is it a solid mass? Is it a giant pool of liquid? It's a fantastic mystery, and setting the stage with this question is absolutely crucial before we begin our journey downward.
Well, to solve that mystery, scientists kinda had to act like global detectives. Since they couldn't just, dig a hole to the center of the planet, they relied heavily on methods of deduction. First off, they gained a massive amount of understanding by studying earthquakes. When an earthquake happens, vibrations or seismic waves pass right through the Earth. And by examining exactly how these waves move, scientists can actually tell if the inside is solid or liquid. They also relied on human observations, like tracking temperature changes in really deep mines, and by drilling massive holes into the crust just to take the planet's temperature. Through all of this, they observed a very, very consistent pattern. Basically, the deeper you go, the hotter it gets.
Here is our roadmap for today's Explainer. 1. Investigating the unseen Earth. 2. The outermost crust. 3. The moving mantle. 4. The extreme core. And 5. Complete chapter summary.
Section 1. Investigating the unseen Earth.
Let's look at a real-world example of this. Think about the Rhosyd Quarry. It's a slate mine located northeast of Porthmadog, in Wales. When miners go deep down into environments exactly like this one, they literally physically feel the heat increasing as they descend. So it's not just some theory written on a page. It is a tangible, physical observation that anyone down there can feel. The interior of the Earth is just much, much hotter compared to the surface, and this localized heat tells scientists that there has to be a massive heat source hiding deeper down. So piecing together all this wave data and those temperature readings, scientists concluded that the Earth isn't just one giant uniform rock. It's actually divided into 3 distinct layers. We have the crust, the mantle, and the core, which is actually further split into an outer and inner core. Definitely keep this overarching mental map in mind as we go ahead and break down each of these layers individually.
Section 2. The outermost crust.
The most crucial thing to remember about the crust is just how incredibly thin it is compared to the rest of the planet. I mean, it varies in thickness from just 5 kilometers to about 70 kilometers. When you think about the thousands of kilometers that make up the entire Earth, this rigid outermost layer is basically like the ultra-thin skin on an apple. But here's the catch. This skin isn't one solid, unbroken shell. It's actually broken into giant pieces called plates, and they are constantly moving. There are 2 distinct types you really need to know about here, the continental plate and the oceanic plate. Under the continents, the crust can be as thick as 40 kilometers, and it's generally made up of older rocks. Meanwhile, under the oceans, the oceanic plates are much thinner. We're talking sometimes as thin as 5 kilometers, and they're composed of newer, relatively younger rocks.
Section 3. The moving mantle.
So, what exactly is causing those massive plates of crust to constantly move around? Well, the answer lies right below the crust, down in the mantle. This layer is absolutely massive, measuring about 2,900 kilometers thick. But the most important characteristic here is its physical state. Unlike the rigid, solid crust we just talked about, the mantle is made of denser rock that is actually semi-solid, so it's not completely solid. And because it sits directly next to the blazing hot core, the mantle gets incredibly heated up, which completely changes how this rock behaves.
Because the mantle is semi-solid, the intense heat radiating from the core creates these powerful convection currents. Basically, loops of heat continuously flow within the mantle, acting as the dynamic churning engine of our entire planet. This continuous motion is the whole reason behind the continental drift theory, which explains that those crust plates we just talked about are constantly being dragged and moved around.
Let's actually break down exactly how this continuous driving process works, step by step. First, the lower part of the mantle heats up simply because it's right next to the core. Because it gets hotter, that semi-solid rock starts moving upward toward the crust. Then, as it gets closer to the crust and further away from the core, it starts to cool down. As it cools, it flows horizontally, right along the bottom of the crust. Finally, that cooler rock becomes denser, sinks back downwards toward the core, gets reheated, and the whole cycle just repeats itself. And it's that horizontal movement along the top of the current that actually grabs and drags the broken pieces of the Earth's crust along with it.
Section 4. The extreme core. The core is the deepest, most extreme environment on our planet, and it's distinctly subdivided into two distinct parts, the outer core and the inner core. The outer core is this layer of extremely dense liquid made up of a nickel-iron alloy, and it's roughly 2,250 kilometers thick. But right in the absolute dead center of the planet is the inner core. This layer is about 1,250 kilometers thick, made up entirely of iron, and get this, unlike the liquid outer core, the inner core is completely solid.
Now you might be scratching your head right now, because the temperature at the inner core is greater than 3,700 degrees Celsius. That is an incredibly hostile, incredibly hot environment.
So the paradox is this: if it's really that hot, like greater than 3,700 degrees Celsius, why on earth is the inner core a solid mass of iron instead of just a melted puddle of liquid? Well, the answer lies in the immense weight of the entire planet pressing down on it. Even though the temperature is way more than hot enough to melt iron, the extreme pressure at the very center of the Earth is simply too great for melting to even take place. The crushing pressure essentially forces the atoms to stay packed tightly together, which keeps the inner core entirely solid.
Now, before we move on to our final review, I want to share a really interesting, kind of surprising fact from your reading. With all these dynamic layers and spinning liquids inside, it turns out the Earth is actually not perfectly round. Because of its rotation and all that internal structure, it's actually slightly flattened at the north and south poles. The specific shape is called an oblate spheroid. It's just a great little detail to keep in your back pocket.
Section 5. Complete chapter summary.
Let's consolidate everything we've learned at a glance. Remember our overarching theme? The interior of the Earth is much, much hotter compared to the surface. First, we have the crust. It's the outermost layer, and it's broken into moving plates, specifically continental and oceanic plates. Next is the mantle. This sits right below the crust. It's made of denser, semi-solid rock, and it's the site of those powerful convection currents that drive continental drift. And finally, the core. This is subdivided into the liquid outer core, made of a nickel-iron alloy, and the deeply pressurized solid inner core, made entirely of iron.
So if you're faced with a blank workbook diagram of the Earth's layers right now, you officially have every single tool and fact needed to perfectly label it. What once might have just looked like a series of empty concentric circles is now totally clearly defined. You know exactly where the ultra-thin crust sits, where the thick churning mantle lives, and exactly where the two distinct layers of the core reside. You are totally prepared to knock this exercise out of the park.
To wrap up today's explainer, I want to leave you with a bit of a thought-provoking question. The next time you step outside and look down at the solid ground, can you actually visualize all that extreme heat, the flowing semi-solid rock, and the immense pressure actively working thousands of kilometers directly beneath your feet? The Earth isn't just some static, boring rock. It is a remarkably dynamic, constantly moving, and intensely hot system. Thank you so much for joining me today, Focus Learners, and I really hope this deeper perspective makes your study of the Earth a lot more fascinating. Catch you next time.